Hello again, ESS. We are back to the last section of our air pollution chapter, and let us hop into it. So the last pieces here are the last two key ideas. Last time we mentioned ozone and how it's very harmful, and we're going to now talk about why we also like ozone when it's way up in the atmosphere. And then we haven't really talked about indoor air pollution. So we're going to go through those ideas today. So key idea number four, let's talk about ozone. So stratospheric ozone, this is the ozone way, 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 way up in the stratosphere. This is the good layer that protects us from ultraviolet radiation. So ground level, and we call that tropospheric, and the troposphere is harmful too. And looks like I forgot to write. Harmful to humans, animals, and plants. It's very reactive. It can damage our lung tissues, and also it's damaging to plants. It's a very reactive compound. However, there is a natural layer of this compound that exists roughly this many kilometers above the Earth, 45 to 60 kilometers, way, way, way up there. So that is no way that's going to come down and hurt us. And this is interesting because it actually absorbs a lot of the really harmful and high energy wavelengths of ultraviolet radiation from the sun. If we didn't have the ozone layer, we couldn't live on Earth. Our bodies would be getting broken down by this all the time. Our skin, our DNA, it's way too reactive, just kind of like X-rays. You don't want a lot of X-rays. We don't want a lot of ultraviolet radiation. Um, some ultraviolet radiation does get through. It's a specific energy, and that's what we still need to wear sunscreen, things like that to protect us. But the even higher energy levels are blocked by ozone. So we want to keep that ozone level as high as possible. So how did it get there in the first place? There's this natural cycle. So there's UVA, B, and C radiation that we talk about, all getting increasingly more reactive. So the UVA is what we think of that comes through very easily. But the B and the C, though, can react with oxygen in the atmosphere. So the cycle is if you have natural oxygen, just normal O2, it can react with UVC type radiation and that can break this down. So this energy from the sun can actually break the bond of O2 and you get these two free oxygen atoms. Then, not all the time, but it can react with another molecule of oxygen. So one of these can react with an O2 and you produce some ozone. So this is a natural process. Some of our atmosphere way up there is made up of a combination of this and oxygen. And then it naturally breaks down over time as well. It can react with this energy of light, UVB and UVC radiation, to actually break the bond to form O2 and oxygen again. So there's this natural cycle of ozone formation that we find in our atmosphere. Here is just one example. There's a lot of studies. It's a little bit tricky to track ozone way up there all the time, but this is one study in Switzerland showing they've been taking these readings since before 1930, and you see they kind of have these natural fluctuations. We had a spike back in the 40s for some reason, but you do see this trend starting from 1970 onward that we're getting quite a bit lower. So from the 1970s downward, we see this obvious downward trend. So that's concerning because we want that ozone layer to be nice and robust to absorb all those harmful radiation. So what's going on here? Well, what we think mostly it's due to human or anthropogenic contributions. So there are some specific chemicals that can go up there and react with the ozone and break it down, the ones that are not naturally going to be there. So the major source of this chlorine that does this reaction are called chlorofluorocarbons or CFCs. These on Earth are very safe. They're very um, unreactive compounds. They're very stable compounds. And that's why they're used in things like refrigeration and aerosol cans. They're used as propellants. They're gases at room temperature. So we use these in refrigeration, air conditioning, in your refrigerators, the coolant systems in your cars, and also we use them as unreactive kind of gases to produce air pockets in specific plastics like styrofoam. And we really started ramping up the use of those when they were created. These are created compounds. These are synthesized. They're not naturally forming. The problem is, over the years, we've noticed that they on Earth are very unreactive. So that means if they escape these products like the cans and the refrigeration units, They're just going to go up into the stratosphere eventually. So CFCs released in the troposphere, they eventually can disperse into the stratosphere. Thanks for that Microsoft email update. Let's see how long that stays there, huh? Okay. Where were we? So what happens then? So they're very unreactive. However, once they get up to the stratosphere, that UV radiation is pretty powerful, and it can actually break the bonds in these CFC molecules, and we get chlorine atoms. And chlorine atoms can work as catalysts and break down ozone. Now, this is important too, why these CFCs are so bad for the ozone layer. They catalyze reactions. That means they can get used multiple times. So let's see how that would work. So if you get chlorine from the CFCs after the radiation, the UV radiation breaks it down, it can actually react with the ozone to produce these chlorine monoxide molecules and then oxygen. So right now, it looks like the chlorine is least used up, right? So it's not going to do any more harm. However, remember that there's free oxygen molecules up in the atmosphere as well. If we go back to this natural process, oxygen also gets broken down into free oxygen molecules, and these are reactive as well. So those can react with the chlorine compound and produce free chlorine again. This is the big problem. This is a catalyst because it's regenerated. So it helps break down O3, and then it's regenerated in the process. And then this can go on and do this process over and over and over again. So the book notes that one chlorine atom can catalyze the breakdown of as many as 100,000 ozone molecules before it eventually finds its way out of the stratosphere. That's the big problem and why these are so bad for the ozone layer. And this depletes the ozone layer over time. So we trying to mitigate this at this point. We have really, it's a lot tougher to get these compounds now. And if they are used, there's a lot more, they're highly regulated at this point. But what we see though, is we've seen about a 10% decrease in the global ozone concentrations. And it happens higher at the poles, north and south poles. So when you hear of like the ozone, the hole in the ozone layer is getting bigger or getting smaller. Well, it does kind of naturally over time fluctuate. So we do see that, but there's some really powerful radiation coming into Earth at the north and south pole. So we get increased amount of this UVB radiation that typically would be reacting with the ozone. However, we are going to see that ozone increase over time if we are very careful about leveling off the use of those CFCs. So that's what's going on with stratospheric ozone, the good ozone. And then ironically, we have bad ozone near us that's created through the photochemical smog process. So that is the last talk about outdoor pollution. Now we're going to talk about indoor pollutants. So especially in developing countries, this is a big problem. It's actually a huge problem. There are so many people living in the world that do not have properly ventilated or efficient fuel burning mechanisms. So remember when we burn things like we have incomplete combustion, we can produce carbon monoxide. And if you're not producing carbon monoxide, you're still producing these particulates in the air if you have these wood, animal manure, or coal inside your little home. So you really have poor air quality in some of these areas of the world. It's really unhealthy. So something that we don't have to deal with, but for indoor air pollutants for developing countries, this is a huge deal. And this next photo shows somewhere, I think in Zimbabwe, but developing African countries, this is a big issue. So this would be, a really inefficient way to cook your food. Just throwing whatever kind of sticks or manure and you're inside your home here, and it's really inefficient. So if it's inefficient, that means you have to use a lot of wood and produce a lot of smoke. So you want to, ideally, you have a better way to do this. And the book mentions this company called BioLite, which I've known about for years. I always see their stuff in camping stores like REI, things like that. But I didn't realize how humanitarian the company was as well until reading through this book. This is a really old picture, obviously. Um, Check out this phone it's charging right now. Looks like a phone I used to have back in the day. We got this charging a flip phone. Clearly this is an old picture, but they've been around quite a while making these stoves where they're trying to make really efficient stoves. that produce less contaminants. And also, this energy is being converted into electrical energy. So the people in the developing countries also have a way to produce light and charge their devices and be connected to the world and get on the internet, things like that. So it's a really cool idea. This is the modern version of that. And actually, this is the model that they produce for the developing countries. And it says this is their flagship stove across India and East Africa, but there's actually, you can buy this on their site right now. They don't typically sell this model to people unless they are part of a special program. So it says the wood burning stove uses 50% less wood than a traditional open fire. And then it also creates this thermoelectric energy where you can recharge this battery pack here. Right now, it's got this little light plugged in that you can charge through USB devices. So it says 90% smoke reduction versus open fire. That is the huge deal here as well. Not only do they have to use less fuel, they're reducing smoke through this special design. It's a very highly designed and engineered stove. So that's pretty cool. Good for BioLite. It'd be fun to get one of these, but they're kind of expensive. So that is developed countries. That's a really kind of the big issue for developing countries. What about, sorry, developing? What about developed countries like America, things like that? We spend, certainly right now and during the pandemic, we are inside so much. So we're sealed off from the world. That means anything in the house we are going to be exposed to. And there are a lot of different things we should be thinking about of indoor air pollutants. This is just a photo of a typical kind of scenario where we have a lot of different sources. So maybe you have wood fire stoves. You could have particulate matter coming from that, even though you have good ventilation. You've got stuff in your cabinets. We have a lot of aerosol things and cleaners, so volatile organic compounds, pollutants, VOCs coming off of sealants or carpets, furnitures, insulation, treated woods, all that stuff that we buy. That can be potentially exposing us to that as well. Paint, older paints that use lead, that's an issue as well. Insulation, we'll talk about this a little bit more, asbestos. What else? Oh, and then radon, which is really interesting. So an actual radioactive gas, radon, can actually come up through the bedrock. So the first one, and this really just shows all the ones that I'm going to talk about here. Asbestos is really interesting because this has been used for since the 1800s. Also, it's been known about since like thousands of years ago. This because it's just a naturally occurring mineral, but it's very fibrous. You can weave it into clothing. You can pack it into spaces around a fire to insulate it. It's very, very resistant to transferring heat. So it was used extensively in homes to use as a natural insulator. However, it was found that these little fibers can get into our lungs and cause extremely harmful health issues. So it's really dangerous, actually, extremely dangerous to have in your home. So if you have an older home before the 1980s it was built, most likely there's asbestos in there unless it was taken out. So that's a big issue. Carbon monoxide, you should always have a CO detector in your home. It's odorless, so you don't understand that it's interacting with you until you see the effects. Radon is fascinating. It's just a naturally occurring gas that's released by different rock formations. And it really depends on the area of the country you're in, and there's higher levels depending where you live. So you should get radon detectors in your house to help understand the levels of naturally occurring radon that are coming up from the ground. And then VOCs, these are fumes comes off of our building materials and plastics, and also from solvents that we might use as well. This is interesting. This is the radon exposure map from the EPA that just broadly shows the risks of radon exposure. And low is this light blue. So down here, the bedrock, not a very high chance of getting much. But notice this upper portion of the United States, especially right this swath through Minnesota and Iowa. Iowa is probably the hot spot of the whole country if you look on a more detailed map. And it's varying degrees, but we're, in that zone. We need to be paying attention about radon in your homes as well. But interesting that it's really dependent on that bedrock beneath your homes. So that is the last piece of this puzzle here. We have gone through, trying to get back to this key ideas, major air pollutants, where they come from, how smog is formed, acid rain. Now we talked about the good ozone, and then indoor pollution. So this is the wrap up for Chapter 10, air pollution. And I'm going to be posting this to the course website, and you'll have some of these review questions to go through to help you study for the next exam. And I'll just keep going for one more second so you can take a peek at those right now if you'd like. All right, I'll see you guys in the next chapter.